Hello. So right now I'm going to describe heat transfer, and I'm going to do this by one, the ways to transfer heat, talking a little bit about that, and then describing each form that we list in one. So starting off, what are the main methods of transferring heat or heat transfer? That is, or one, that is conduction. Two, convection. And then three, radiation. What are the main ways? Well, this is in exchange from like momentum P, energy E, and mass M. And of course, heat, as we talked about before, is measured in terms of joules or energy. Here's a bit of a diagram. As you can see, the radiation is from the flame, like the heat from the flame. The convection is the liquid within the pot, and the conduction is from like on the handle as it gets hotter from the fire. But let's talk more about what this picture means. And moving to the second part right here, where we will describe each form. So let's first start with conduction. Conduction is the process where heat is transferred through neighboring collisions between atoms or molecules, normally associated through solids. So basically, heat transfer through, we're just going to say through solids. That can be a bit simplified as it can be through other ways, as said before, collisions between atoms. But for right now, we're just going to keep it at pretty straightforward, simple for this. But of course, it can be through other states of matter. So through this, we're also going to look at Fourier's law, which talks a bit about this, where he labels Q, which is vector, is equal to minus K multiplied by the gradient of T, where the gradient of something, in this case temperature, is change of temperature in respect to X, Y, and Z. So each spatial dimension, essentially. This would be in 3 dimensions. But what is Q? Well, we should always use, dimensional analysis in any physics problem. That is always normally, dimensional analysis gets you pretty far. So K is the material's thermal conductivity. What is that measured in? Is measured in joules per second, meter Kelvin. And temperature, or the gradient of temperature, is by temperature, which is Kelvin. And then we're looking over each spatial dimension. So it's going to have a unit of length underneath it, or meters. What does this get together? These would, for example, cancel out. These multiply together. Well, we get energy flux. So this is really just energy flux. Why? Because something per second area is the flux, and of course we're looking at the energy from the flux, so energy flux. And again, to preface, K is the materials thermal conductivity. Conductivity. Cool. Now let's look at convection. So what is convection? Heat transfer. Transfer through fluids mostly. Where can fluids be from? Fluids can be from, example, liquids or gas or both or something similar. Definitions of fluids are actually quite interesting, which I actually might want to talk about at a later time. I'm going to make this a little bit more clearer. Transfer. Now, there are two main types of convection. There is natural versus forced convection. Natural is due to buoyancy, buoyancy or density. So essentially, things that are lighter go further up. Things that are more dense or heavier go further down. Essentially, just lighter things rise, denser things fall or sink, or just heavier things sink. That is a natural form of convection. We see this in the atmosphere, many different ways. And then forced is through an external force or an external source, forcing, undergoing convection. To look at forced, so let's look at forced. We'll look at Newton's law of cooling. So Newton's law of cooling essentially states that right here, the energy per time is equal to HA. H is the convective heat transfer coefficient, A being the area, and then the temperature. This temperature is also a function of time, as we can see that there's a function of time right here as well, subtracted by the temperature of the environment. So put that in perspective, H, convective heat transfer coefficient, and T, the first T, function of temperature, is the temperature from the fluid's surface. The temperature of the environment is the temperature of the environment. So environment temp. And then the area specifically is where the heat transferred surface area. So that particular area. Now, looking at this through dimensional analysis, because we always should look through dimensional analysis, dq over dt, what is that going to be in units? That is going to be in joules per second. So we should get joules per second on the other side, where the units of H, the convective heat transfer coefficient, that is joules per second meter squared per Kelvin, so per temperature, area meter squared, as we already know, and then the temperature, you already know it, it's just Kelvin. So what does this actually mean? Well, joules per second. So first off, we can see that these cancel out. So we do in fact get joules per second, which is good. What is this? This is energy rate. Because if something is per second, it's the rate of something. Speed, velocity is the rate. And we've seen joules per second before. That is power, the power of something, with like the work per time. Now we're going to talk a little bit about radiation. I'm actually going to do radiation much more in depth. So I'm not going to go over much here, as that will be talked about in a future video, because radiation is quite interesting. But it is from emission or transmission of energy in the form of waves or particles. Waves or particles kind of makes you think of quantum mechanics. And it is going to be through a medium or space, vacuum, so on and so forth. So radiation is actually incredibly interesting. We will go over more of that in the future. So this will be a future thing to look forward to. But anyhow, thank you so much for listening, and I hope